electron cloud. Now let's first start off differentiating between the quantum mechanical model and Bohr's model. Now, Bohr's model came first. Bohr looked at the sun and looked at the planets and said, here's the sun and the planets go around the sun, just like that. And then he looked at the atoms and said, I bet that's how the electrons move. The nucleus is in the center, and I think the electrons move around on paths just like planets go around the sun. And just like we can predict exactly where a planet's going to be at any point in time, he thought that we can predict where an electron's going to be. That is not right. So he stated that electrons travel around the nucleus on a predictable path and can be found in specific locations. That's not right. It worked awesome for hydrogen, because hydrogen only has one electron, that's it. So his model worked well for that, but it didn't work for other elements. So scientists kept refining the model of the atom, and they eventually came up with what we believe today as the quantum mechanical model. Now, this is a very simplified answer here, but the quantum mechanical model is based on probability and math. Tons of mathematical equations predicting where electrons are probably found. They're probably found in certain regions of the electron cloud. Remember, we had the S sublevel. The S was round. So we don't really see like a container for these electrons, but we do know if here's our nucleus and we have the electrons around it, that if the electrons are in the S sublevel, we could take pictures of where they are all the time. The picture would kind of look like this. And if you step back and look at what shape that is, it kind of looks like a circle. And the P sublevel, again, if the nucleus is this little center and the electrons are zipping around, we know that if you stand back and take a look at where the electrons typically are, most of the time, not when they get really excited and gain lots of energy, but where they typically are, then it looks kind of like a figure 8. And the D kind of looked like a clover. I don't want to draw all those dots. And the F was crazy complex. Lots and lots of weird shapes. So this is what scientists did. They kind of figured out where the electrons spend most of their time. They're probably in a certain region of the electron cloud, but we don't know exactly where. Just like if you knew, here's some blades of a propeller, and the propeller starts spinning, you basically just see a blur in this area. And if I said, tell me where the blades are now, you wouldn't know, are they here, are they here, are they here, where are they? You just know that they're here and probably not here. They're in this blurry area. They're probably not outside it. So you can narrow down and use some probability to figure out where these blades usually are. But we don't know exactly where they are within that region. So we have these energy levels. The energy levels are kind of like rows of the theater. Then we have, within the rows, we have what we call sublevels. Within the energy level, we have a sublevel. The energy level is broken down into parts. Now, if you're in row 1 of the theater, you just have the round S seat. If you're in row 1 of the energy level, you just have the S shape, the S sublevel. If you're in row 2 of the theater, you have the S and the P seats. If you're in the second energy level of the electron cloud, you have the S and the P. You have all those places for the electrons to hang out, and so forth. If you're in 3, you have SPD. If you're in 4, you have SPDF, and so on. Now, each of these sublevels can hold a maximum number of electrons. It can hold less, but it can't hold more. S can't hold any more than 2. P can't hold any more than 6. D can't hold any more than 10. And F, sorry about that. Where'd it go? And F can't hold any more than 14. And if you forget those numbers, just look on a periodic table. The S section, oops, there we go. The S section is over here, S1, S2. Let me erase all this mess here. So here's S1, group 2 is S2. The P section's here. This is P1. These guys all end in P1, all the way over to P6, right here. The D section's down here, D1 all the way over through D10. And the F section is down here, F1 through F14. So there's a lot of organization in this periodic table. And again, if you forget how many electrons are in each sublevel, just look. It's right there for you on the periodic table. All right. Oops. Now, the off-bow principle. If I said, start telling me the ABCs, hopefully you would start with the letter A, and you would tell me B, and then C, and D, and you would go in order. So you probably start with the letter A and go in order. If I tell you, or ask you to tell me where the electrons are, you would start with the lowest energy level. You would start telling me where the first electron is and the second one and so forth, and you would do them in order of energy. Just like when we use the theater analogy, we fill the seats based on money. We fill the cheap seats first. Cheap seats first. Then we went to the back of the theater where the really expensive seats were. But we did those after the cheap seats were filled. So when we compare an electron in the 1s sublevel with an electron in the 3s, we know that this one has more energy than this one. This has less energy. So the closer you are to the nucleus, the less energy you have. The farther you are away from the stage or from the nucleus, the more energy you have. Now, knowing all that, we should be able to write the electron configuration for the following elements. We should be able to find out where the electrons in chlorine spend most of their time. So this is where you need your periodic table. You're just going to basically run your finger along the periodic table or run your pen along the periodic table, and you're going to write down the information whenever you get to the end of a section. So the first thing you get to is the end of 1S2. This is S2 over here. Technically it should go here, right there, like the rest of the S2s. But helium, he's special. He's got 2 valence electrons, so he gets to hang out with the big guys, with the noble gases. So 1s2. Then we come to the second row. We start here. We get to the end of the S section. We write it down. 2s2. Keep going. Now we get to the P section. This is a P block. We're still in the second row. So we write 2p6. Because there's 6 of them. Then we're done with the second row. Now we go to the third row. Start over here with the S again. So we write 3, this third row, S, and we're going to fill up both, S2. Then we jump here to the P section. We're still in the third row, 3p, but we're going to stop when we get to chlorine. Chlorine is right here, P1, P2, P3, 4, 5. There's chlorine, so 3p5. So that's that example. Now, if we were doing iron, iron's a little bit farther down the periodic table than chlorine is. So we're going to have to keep going. We're not going to stop when we get to chlorine. We're going to start off. Row 1, S seats, 2. Beginning of row 2, S seats, 2s2. 2p6. All 6 of them. Now we're done with the second row. Let's go to the third row. 3s, 2. Then we keep going, going, going. Now we get to here. We're in the third row. This is the P section, and there's all 6. 3p6. We're not at iron yet. Iron's over here. We got to keep going. We're almost there, though. Fourth row, right at the beginning. What comes first? The S section. So 4s2, right there. And then we get to the D section. This is the D block. D's are always 1 behind. So this is in the fourth row of the periodic table, but this is the 3D section. So after 4s2, it's 3d, oops, not 10, my bad here. It's 3d1, 1, 2, 3, 4, 5, 6. 3d6. And that's the electron configuration for iron. All right, let's now look at the orbital diagram for the following element. Well, in this case, we have sulfur. So the orbital diagram is a little different because it asks you to draw arrows. So basically, you do the same thing, you just draw arrows for everything. Now, sulfur is over here. It ends in the third energy level. So it ends in 3, it's in the P block, and it's P1, 2, 3, 4. 3p4. So you know in the 3p section you're going to have 4 arrows. Everything else before that has to be completely filled. You can't have electrons here if these guys aren't filled before it. That's the off-bow principle. So basically, just draw an arrow up and an arrow down all the way across till you get to 3p, and over here, just draw 4 electrons. Now do arrow up, arrow up, arrow up, and then double up. It's kind of like people getting on a bus. If there's 3 empty seats and 4 of you come in, if you're all strangers, you're probably all going to spread out, and then somebody's going to have to double up. But you wouldn't want all these strangers sitting on top of each other and leaving an empty seat here. That would be silly. So put 1 electron in each because they're negatives, they're electrons, they repel each other. Then double up if you have to. So there's your orbital diagram. Now, what do the following elements end in? So we've got barium. Barium is over here. It ends in 6, and this is the S2 column. So 6s2. Here's silicon. Silicon ends in P2. Well, it's the 3rd row, so it's 3p2. Bromine, there's bromine right there, and it's P5. 4p5. And radon is right there. This is in the P6, and it's the 6th row of the periodic table. So it's 6p6 right there. 6p6. So you should be able to predict what everything ends in. And remember, if this ends in S2, so does this one, and this one, and this one. If this ends in P5, so does this one, and this one. If this ends in P6, so does this one. The electron configuration, what they end in, determines the properties of these elements. So all these elements in the same group act the same way because they have the same electron configuration. All right, let's take a look at question 7. Question 7 says, use the abbreviated or noble gas shortcut to write the electron configuration for the following elements. So here's aluminum. Now, when you write the electron configuration with the shortcut, you have to go back, back, back. So this is 13, you go 12, 11, and then 10. This is the noble gas. Here's neon in brackets, and then you write whatever you have to write, or whatever you have to pass through to get to aluminum. So this is 3, we'll start at the beginning of the row, 3s2, and then you get right there, 3p1. Strontium. Strontium is right here. It ends in 5s2. So we're going to go back, back, back. There's 38. We're going to go to 37, 36. So we write krypton in brackets. That takes care of 36 electrons. And then all I have to do is pick up at the beginning of the row that strontium is in. So I pick up in row 5, section S, and it's S2. So I put that there. So use a noble gas that comes before it, and then pick up at the beginning of the row that that element's in. And determine the valence electrons. So when you figure out valence electrons, you're basically going to be looking for the coefficient that's the highest. So pretend you're walking in the theater. We see people in the first row, we don't care about them because there's people behind them. We see people in the second row. We don't care because there's people behind them. But there's nobody in the 4th row. This is empty. So we don't worry about that. We only care about the people in this example, in the 3rd row. So 3s2, 3p1, you add them together, and you get 3 valence electrons. And that makes sense because 3p1 is over here. This is p1, p2, and so forth. So these guys, P1s, are all in group 3, which is why it's got 3 valence electrons. Here, we don't care about the people in the 1st row because there's people in the 2nd. We don't care about people in the 2nd because there's people in the 3rd. A lot of them, 2 and 6 and 6. But we don't care about them because there's 2 people in the 4th row. We only care about who's in the last row. There's 2 people in the 4th row, so there's 2 valence electrons. 4s2, we're going to worry about those 2 valence electrons when it comes to bonding. Group 1 elements. Group 1 elements all have 1 valence electron. Neon. Neon's over here. Neon's in group 8, so it's got 8. Aluminum, right there, in group 3, so it's going to have 3. Magnesium, right there, in group 2, it's going to have 2.